And what we want to now talk about is what happens if the electric field is not uniform, if the field is actually changing along different parts of the path. And we'll look at a couple different cases. And the first is the simplest case, where we just have a case where, say, the path goes through different regions, or goes through regions of different uniform electric fields. Okay. So, for example, if I have some part of the path, let's say in this region, there's point A and there's point B, and along A to B, let's say I know the electric field is pointing in this direction, call it E1, okay, and it's uniform throughout this entire region. And then from B to C, which is here, let's say I have a different electric field. It's uniform within that region. No, it's the same color, it's okay. But we'll call this E2. So I measured just a different electric field in this part of the space. And we can even have a third region from D to C to D. Call this, I don't know, E3. Maybe it's even off in some direction. Like so. And we want to find the potential difference, potential at D minus potential at A. So this means a path that goes from where to where, starts where? Starts at A and goes to D, right? Final minus initial. So our path goes like so. Okay? So what do? How do I calculate the total potential difference across that path? Break it up into pieces, right? Break it up into regions where I know how to calculate the potential difference for a uniform field, right? So A to B, the field is uniform, it's E1. And then from B to C, it's a different field, but it's uniform, E2. And then C to D is E3. So I could calculate the potential difference from A to B, and then B to C, and then C to D. So if I want to write this out as, VD minus VA is equal to potential difference VB minus VA plus VC minus VB plus VD minus V sub C, okay? And so I'd have negative E1 dot delta L1, call it, okay? Delta L1 being the vector that points from A to B, the path vector that points from A to B. And then from B to C, we have a delta L2, and then C to D, a delta L3, okay? So we just add those up. Okay. And if we had other regions continuing, we just keep on doing the same thing, okay? Adding up the potential difference across each part of the path where we know the field is uniform within that region, okay? So it seems pretty obvious, but people often make mistakes. They sometimes want to average the fields out somehow across the entire path. Don't do that, okay? Don't do that. Just break it up into steps and calculate the potential difference across each step, okay? So let's try an example. Where would we see a situation like this? So we have some region of uniform electric field over here that is 300 volts per meter pointing in the positive x direction. And then we have some region here where the electric field is 0, and some region here where the electric field is 300 volts per meter pointing in the negative x direction. The distance from point A to this surface is 0.02 meters. This distance is 0.03 meters, and then this distance is 0.04 meters to B. First of all, could we have a situation like that? What is this? What's going on here? You have a region where You have a uniform electric field on one side, a uniform electric field on the other, and it's 0 in the middle. So what could this possibly be? Yeah. It could be a capacitor, little even simpler than that, right? Just a block of metal, or maybe one plate, right? Just a disc, right? If you had a metal disc, okay. Well, first of all, what do we know about the charge on the metal disc? What's the sign of the charge on that metal disc? It's negative, isn't it? Because the field is pointing towards the surfaces. So what if we had a negatively charged metal disc that had some thickness? This is metal. So inside of metal at static equilibrium, the net electric field is equal to 0. But if we're near the surface of the disk, then the field is uniform across the surface. And if it's negative, it's negatively charged, it's pointing towards. So this is possible. Okay, we can have a situation like this. We're not showing the entire disk, but we're showing some section of it. So let's try it. Based on what we just did, see if you can calculate delta V, the potential difference VB minus VA, which is the path that goes from where to where? A to B, right? Final minus initial. Okay, try it out. Oh, a little bit of disagreement here. Okay, so maybe this isn't as obvious as we thought. So let's take a look. Most of us are saying, let's see, the most popular answer is answer 3, 6 volts. But some people are saying negative 6 volts. Some people are saying negative 18. So let's see. We have a situation where we have 0 volts per meter inside this metal block. And A is here, and it's 0.02 meters away from the surface. This distance is 0.03 meters. And then the distance from the surface to B is 0.04. Okay. So, electric field on the left side is pointing in the positive x direction, 300 volts per meter. Negative x direction on the other side, 300 volts per meter. Okay? And our path goes, we said we're starting at A and we're going to B, right? So I'll just pick a path that goes along a straight line. It goes straight through the block, directly over to B, right? Okay. How many different regions do I want to break this up into? 2? 3? 2? 3? Well, one region has an electric field that is equal to 0, right? So that region is going to be easy to calculate, but it's still a region that we're going through, right? If we're imagining traveling along a path that goes from A to B, we traverse through this region of 0 field. So we should take it into account. Okay, calculationally it's going to be simple to deal with, but it's still 3 different regions of uniform field. Okay, so from A to the surface, from the surface to the other surface, and then from the surface to B. Okay, so let's break it up into 3 sections. We have VB minus VA is going to be negative E1 delta L1 plus or minus, we're adding a negative here, minus E2 dot delta L2 minus E3 dot delta L3. Okay. So negative. How would I write E1 as a vector? This is E1, right? And this is E2. And over here is E3. So how do I write E1 as a vector? 300, 0, 0. How do I write delta L1 as a vector? 0.02, 0, 0. Okay? All right. vector E2 is just, or electric field E2 is just 0, 0, 0, right? Dotted with that path. It's not going to matter much. And then lastly, the electric field in region 3 is what vector? Negative 300. So we have a minus, a negative 300, 0, 0, dotted with 0.04, positive 0.04, 0, 0. Okay? All right, and this is, the units volts per meter times meters, volts per meter times meters. We're going to get units of volts, okay? So I get what? This is going to give me negative 6, right? This is going to give me 0. And this is going to give me what? I'm subtracting, and I have a negative 300 times 0.04. That gives me a negative 12, right? Negative 12. And then if I have a minus times a minus, that's going to give me positive. So I end up with the total potential difference is 6 volts, positive 6 volts, okay? So you can see once again what happened. Lost the negative sign there. Is that that's where the negative 18 came from for a lot of people, right? So that's easy to do. How can we check it? Well, remember what we talked about last time. If I'm going in the direction of the electric field, I start at A. Imagine sort of walking along this path, or imagine a positive charge moving along this path, okay? You start at A, and you're going in the direction of the electric field. That should give you a potential difference that's positive or negative. If you're going in the direction of the field, the potential goes down, right? It's actually negative, okay? So remember, well, we just erased it, but delta V is negative when electric field and delta L are in the same direction, okay? So again, the way to think about that is if you let a positive charge go on its own, it would move in the direction of the electric field. There would be positive work done on it. Its kinetic energy would increase. The potential energy then would have to decrease. So the potential would have to decrease, right? Okay, so that's got to be negative. Go through here, you get 0. But now you're going in the opposite direction of the electric field, so the potential on that side should be positive, right? So delta V is greater than 0 if the electric field and delta L are in the opposite direction, okay? So again, the point is check it, okay? It's easy to make sign mistakes. Check it as much as you can by looking at what the sign should be based on the physical situation, okay? So 6 volts, number 3 is correct.